Welcome to Talk Tensors, the podcast where we really get into the details of cutting-edge machine learning research.
Great to be here.
Today, we're diving deep into a really fascinating paper, Siamese Foundation Models for Crystal Structure Prediction. Now, predicting how atoms arrange themselves in a crystal furrow, why should we care? Well, this whole problem, crystal structure prediction, or CSP, it's actually a major bottleneck.
It really is.
Yeah, especially for discovering new materials, things that could, revolutionize tech like faster semiconductors or better catalysts.
Think of it like protein folding, but honestly, maybe even more complex in some ways.
Right. And AI tools like AlphaFold, they've made huge leaps in protein structures. But CSP, it's remained stubbornly difficult.
Yeah, the traditional methods are often really, really computationally intensive.
Heavy lifting.
Exactly. And this paper, it's proposing a new machine learning way forward that might just change the game.
That's the hope. For decades, CSP relied on things like first principles calculations, stochastic sampling, evolutionary algorithms. Powerful stuff, but slow.
Powerful, yes.
Yeah.
But they demand serious computing power, and they just don't scale well when crystals get complicated. Deep learning seems like a potential shortcut.
Learning from data we already have.
Exactly. Learning patterns from existing crystal databases, and we've seen deep generative models pop up for crystals.
But they had limitations too, right?
Yeah. The issue often was they relied on pretty small, sort of domain-specific data sets, so their ability to generalize to predict truly new stuff was limited.
Okay, so limitations with the old ways, limitations with the newer ML attempts. That brings us to this idea of foundation models.
Right. These huge AI models pre-trained on massive data sets. They've been incredibly successful in language images.
And now the idea is to apply them to material science.
Yep. People are trying to use them to predict forces between atoms or just generate crystal structures generally.
But what's interesting about this paper we're looking at today is that a lot of those previous foundation model attempts for crystals didn't specifically target CSP, figuring out that stable 3D structure from just the chemical formula as their main goal.
Precisely. And that's where Siamese Foundation Models for Crystal Structure Prediction really comes in. The authors introduced this new framework, DAO. It's explicitly designed for CSP using a pre-trained fine-tune approach.
DAO, and it has two parts.
Two main Siamese networks, yeah.
Wow.
DAOG, the G is for generation, I guess the structures. And DAOP for prediction, predicts their energy.
And they're both built on something new.
Both use a novel geometric graph transformer called Christformer. Now, Christformer is pretty smart.
How so?
Well, it's designed to understand that crystal structures are the same no matter how you rotate them. That's O3 invariance.
Okay.
And it gets the repeating pattern, the periodic nature of crystals. These are fundamental properties, and Christformer respects them inherently.
So our mission for this deep dive, understand how DAO, with this generator and predictor, and the Christformer backbone, gets past the old limits.
Yeah, how does it hit these state-of-the-art results, and could it really, shake up materials discovery?
Let's get into it. The paper's core ideas and why they're making waves.
Okay, so the core problem. You have a chemical formula, like ingredients. How do you predict the stable crystal structure it forms? Accurately and crucially, efficiently.
And DAO is their answer.
DAO is the proposed solution. The framework with DAOG and DAOP, the Siamese models, built on Christformer.
And the key strategy is pre-train fine-tune.
Right. DAOG, the generator, gets pre-trained on this huge data set, ChristDB. And here's a really interesting twist.
Yeah.
ChristDB doesn't just have known stable crystals. It also includes a lot of non-stable ones, hypothetical structures.
Wait, really? Why train on unstable structures if you want stable ones? That sounds counterintuitive.
It does a bit, but that's where DAOP, the energy predictor, plays this really clever role during pre-training.
Yeah.
They call it dataset relaxation. Basically, DAOP estimates the energy of those non-stable structures in the database.
Right.
And that energy information is used to kind of nudge the atoms in those unstable structures, gently push them towards more stable, lower energy arrangements.
So it lets DAOG learn from a much wider variety of possible crystal shapes, not just the ones we already know are winners.
Exactly. It learns from the right answers and the wrong answers, but also how to sort of correct those wrong answers. It learns a broader energy landscape.
Okay, that's clever. And the paper shows this actually works, right, on the benchmarks?
Absolutely. They tested DAOG on standard CSP benchmarks, things like MP20 and MPTS52, and it's significantly beat the existing state-of-the-art methods.
Beat them how?
Much higher match rate, meaning it found the correct structure more often. and lower RMSE, root mean square error. So even when it wasn't a perfect match, the predicted atom positions were closer to reality.
Impressive. But did they just test it on benchmarks or real stuff?
They went further. They applied DAO to predict structures and properties specifically, critical superconducting temperatures for 3 real-world materials: CSV3sb5, ZR16RH804, and ZR16PD804.
And these are tricky material.
Known to be quite complex,
Yeah, right.
challenging computationally.
Mhm.
And DAO, it nailed the structures accurately.
Wow.
And did it much faster than traditional methods like Quantum Espresso. Plus, it predicted their superconducting transition temperatures really well, too.
Okay, hold on. Outperforming something established like Quantum Espresso, which needs massive compute time on complex, real materials.
By a significant margin, according to their results.
That really does sound like more than just an incremental step. It sounds like it could genuinely speed things up.
That's the potential impact, exactly.
Yeah.
A powerful, efficient ML tool for predicting structures could dramatically accelerate the whole materials R&D pipeline, finding new materials faster.
Okay, to really appreciate DAO, maybe we should rewind a bit. Look at the history that led up to this. CSP wasn't born yesterday.
Oh, definitely not. This quest to predict crystal structures, it's fundamental in material science, goes way back to the 1950s.
So decades of work.
Decades. Researchers used chemical intuition, rules learned from observation, and then increasingly complex computational tools.
We mentioned the comparison to protein folding earlier.
Right. And while protein folding saw huge progress with AI, CSP advanced more slowly. Part of the reason is just the sheer diversity of geometries and symmetries crystals can have. It's arguably a more complex space than proteins.
So before deep learning really took off in this area, what were the main tools?
Well, initially it was based on crystallography principles, rules about how atoms like to pack.
Yeah.
Then came more physics-based methods.
Like simulations.
Sort of energy minimization using intertonic potentials,
Yeah.
basically mathematical formulas for forces between atoms, and density functional theory, DFT.
DFT is pretty standard, right?
Very standard and quite accurate for stability,
Mm-hmm.
but incredibly computationally expensive. You couldn't really use it for large, complex systems or high-throughput screening easily.
So limited scope.
Exactly. Then people started using data-driven approaches, mining the growing databases of known crystals for patterns. But those often struggled with predicting truly novel structures, things very different from what was already known.
And then deep learning comes onto the scene. How did that change things for CSP?
It offered a totally different angle. Deep generative models, like diffusion models or flow models, showed real promise. They could learn the complex statistical distributions of crystal structures directly from data.
You mentioned diffusion models. How do they relate?
Well, the authors note this too, the way diffusion models work, by starting with noise and gradually refining it into a structure. You can kind of think of that denoising process as acting like a force field, guiding atoms towards stable spots.
Interesting analogy. But even these DL models had issues.
Yeah, as we said before, often generalization was tricky. High performance on benchmarks wasn't always consistent, partly due to being trained on maybe smaller, more specialized data sets.
Which naturally leads to the idea of foundation models for CSP.
Exactly. Leverage much bigger, more diverse data sets to learn more general representations, like we've seen work wonders in NLP and vision.
So people started trying this for crystals.
Yeah, several groups started exploring crystal foundation models. They generally fell into 2 camps.
Okay.
One was supervised learning, training networks to predict those interatomic potentials, the forces, which you can then use in simulations.
Right, predicting the physics.
The other was more self-supervised, learning general representations of crystals for various tasks predicting properties, or even generating new crystals, like the MatterGen model the authors compare against.
So where does DAO fit in this picture? What makes it different from MatterGen or this potential predicting models?
The key difference is that DAO directly targets crystal structure prediction itself as its main pre-training task.
Ah, okay. Not just general generation or force prediction.
Exactly. Unlike MatterGen, which might have broader goals about composition, symmetry, properties, DAO's pre-training is laser-focused on predicting that stable 3D atomic arrangement.
And the other key difference?
The data. Remember, CrisisDB, pre-training on both stable and a large number of unstable structures. That's pretty unique. It lets it learn from a much wider range of possibilities, especially combined with that relaxation step. So the specific focus on CSP plus the unique training data strategy really sets DAO apart.
Right. Which brings us nicely into the novel notions and extensions part. This is where they really dig into the unique mechanics and future potential. Let's start again with those unstable crystals in the training data, SDB.
Yeah, it's a core idea, and how they handle the potential problems of using so many unstable structures, about 640,000 unstable versus 300,000 stable, roughly.
So more unstable than stable.
In their initial data set, yes. And the key is DAOP and that data set relaxation.
Okay, remind me how that works again.
DAOP predicts the energy gradients for these less stable structures. Think of it like predicting which way is downhill on the energy landscape.
Right.
That gradient information then guides an optimizer, LBFGS in this case, to gently shift the atom positions in those unstable structures, nudging them towards lower energy, more stable spots.
So it's like computationally annealing them.
Kind of, yeah. Figure 3C in the paper actually shows you see a clear shift towards lower energies after relaxation.
So DAOP acts like a guide, helping these hypothetical crystals find a better configuration.
Pretty much. And it's not just a one-off thing. The pre-training for DAOG happens in 2 stages.
2 stages.
Stage I is pre-training on the whole, ChristDB, stable and unstable included. Then comes the relaxation step using DAOP. Then Stage 2 is further pre-training, but now on the relaxed data set.
And this 2-stage process helps.
Their ablation studies, shown in Figure 3A, really highlight that including the unstable crystals and using this 2-stage approach significantly boosts DAOG's final performance on the CSP benchmarks. It learns more effectively.
Okay, and DAOG isn't just finding one structure, is it? The paper mentioned polymorphism.
That's a really important capability. Polymorphism, where the same chemical formula can form different stable crystal structures, is crucial in material science. Different polymorphs can have wildly different properties.
And DAOG can find these multiple structures.
Yes, Figure 3B shows an example, NENA 602F10, where DAOG generates 4 distinct conformations, different polymorphs. And the accuracy for each, the RMSE, is really low. So it captures that diversity well.
Now, DAOP, we talked about dataset relaxation, but it does more, right? It guides DAOG during generation too.
Exactly. That's the energy-guided sampling. When DAOG is actually generating a new structure step by step in the diffusion process,
Yeah.
DAOP jumps in and predicts the energy of the structure as it's being formed at intermediate steps.
Okay. And what does DAOG do with that info?
It uses that predicted energy to steer the generation process. It biases the steps towards lower energy, more stable configurations.
Like a quality control check during creation.
Sort of.
Yeah.
And figures 3E and F show this works. Using energy guidance leads to generating stable structures much more often and gets lower error on that tough MPTS 52 benchmark.
Are there examples?
Yeah, figure 3G has some striking ones like CS2YB22S6. With energy guidance, it gets the structure right. Without it, it fails. The guidance makes a big difference in stability and accuracy.
It's like DAOP is whispering to DAOG, that looks a bit unstable. Try nudging those atoms this way.
Yeah, that's a good way to put it.
Okay.
And this pre-trained DAOP model turns out to be useful for more than just guiding generation or relaxing data sets.
Oh, what else can it do?
They tested its ability to predict other crystal properties beyond just energy or stability.
Like what kind of properties?
All sorts. Figure 4 and Table 4 show results on 8 different data sets, things like electronic band gaps, dielectric constants, even mechanical properties like how stiff or compressible a material is, shear and bulk moduli.
And how did it do?
Really well. It achieves state-of-the-art or very competitive results on most of them, just by fine-tuning the pre-trained DAOP. It showed a big improvement on predicting energy above the hull, Jarvis Hull, another stability measure.
That's impressive versatility from the predictor model.
No, and it even did well on a small data set, JDFT2D, suggesting it's good at few-shot learning from limited examples.
Okay, and then there's the superconductor application we touched on earlier. That seemed like a major validation.
It really was a great showcase of DAOG and DAOP working together. First, they fine-tuned DAOG on a superconductor dataset, SuperCon3D, to generate structures.
Right?
Then they fine-tuned DAOP to predict the critical temperature, PC, the point where superconductivity kicks in.
And they did something clever with the training data.
Yes. They actually augmented the training data for DAOP using structures generated by DAG itself. And that boosted the accuracy of the TAC predictions even further. You can see that in Figure 5A and C.
Using generated data to improve prediction. Nice feedback loop.
Exactly. But the real kicker was testing it on those 3 new real-world superconductors it hadn't seen before.
The CSV3-SP5 and the zirconium ones.
Yep. DAOG predicted their complex structures really accurately low RMSE. And DAOP predicted their critical temperatures with impressively small errors. That's Figure 5D and Table 6.
And this is where the comparison to traditional DFT like Quantum Espresso really stands out.
Yeah, Table 8 and Figure 6 in the supplementary info apparently show the challenges DFT faces with these complex materials, highlighting DAO's efficiency and accuracy advantage here.
Okay, seeing all this work, what are the next steps, the extensions they suggest?
Well, one really neat idea is extending that energy guidance principle.
How so?
Right now, DAOP guides towards stability, low energy. What if you could guide towards other desirable properties?
So instead of just make it stable, it's make it stable and stiff, or stable and dues have this electronic property.
Exactly. You could potentially fine-tune DAOP to predict, say, shear modulus really well, then feed that prediction into DAOG's sampling process to bias it towards generating stiffer materials. Active design through generation.
That sounds powerful. Moving from prediction to targeted design. Any other big ideas?
They also speculate about applying the whole DAO framework, the Siamese models, geometric transformer, guided sampling to other scientific areas.
Beyond crystal.
Yeah. They mention proteins again. Maybe not just predicting structure, but using similar ideas for interactions or function based on substructures. Or even totally different fields like designing material microstructures or metamaterials. Anything with complex, repeating geometric patterns.
The core concepts might be quite generalizable.
That's the suggestion. The synergy between generation and prediction, guided by specific objectives, could be broadly applicable.
Okay, fascinating possibilities. So if we wrap up our deep dive, what are the absolute key takeaways from this DAO paper?
I'd say the big thing is that this DAO framework represents a really significant step forward for crystal structure prediction. It offers this balance of accuracy and speed that was hard to achieve before.
Outperforming the state of the art.
Right. And the key innovations are the Siamese Foundation Models, DAOG and DAOP working together, the smart pre-training on diverse data, including unstable structures, the effectiveness of dataset relaxation, and that energy-guided sampling.
And the versatility.
And the versatility, yeah. Good for structure generation, good for property prediction. As shown with the superconductors, it's a well-designed, integrated system.
It really does feel like a substantial advance, applying these sophisticated ML ideas to a really tough, fundamental material science problem. So maybe a final thought for our listeners.
Go for it.
Given how well DAO tackled the complexity of crystal structures, it makes you wonder, right, what other big scientific challenges, the ones currently stuck because of computational limits, could be cracked open by developing these kinds of tailored foundation models? Where else could co-design, generation, and prediction accelerate discovery?
It's a great question. The potential across different scientific fields seems huge. Definitely worth thinking about. We'd certainly encourage listeners to check out the paper itself and explore computational materials science more if this sparked their interest.
It's a super active field right now.
Absolutely. And DAO is a very exciting development within it.
Well, thanks for joining us on this deep dive into DAO and crystal structure prediction. We'll be back soon with another look at cutting-edge research.